Welcome to the last video of chapter 13. Woo! We made it. Last video is going to cover velocity and acceleration. So those of you who've taken physics, some of this you've probably seen in physics before. Some of it might be new or might look new. As you can see from the timing on this video, it is a little bit of a doozy. There's a lot to cover similar to the last video. So let's stop wasting time and let's just jump in. Let's say that we have some curve C that is a vector valued function denoted by r of t, and this is a position function. So let's say that at some time t, we are somewhere on this curve and we are moving along the curve. We're going to take a look at some background. First piece of background is the direction of motion at any time is always in the direction of the unit tangent vector. And that should make sense. If I draw in my unit tangent vector, we can see that that's the way that the point would be moving as time is increasing. The other thing for us to know is speed is ds dt. So little s is arc length. So this is the rate at which arc length is changing with respect to time. So it's the instantaneous rate of change of arc length, and that's a scalar. Now the velocity vector is that ds dt, the speed, times direction. So ds dt, remember, is the magnitude of our velocity vector, and then the unit tangent vector denotes direction. So altogether, what that's telling us is that our velocity vector points in the direction of motion, so that's our unit tangent vector, and has magnitude equal to the speed of the particle. And that you've seen before. Okay, so then next up, if r of t is our position function, like we've already said, the way that we find velocity then is we take the derivative of the position function with respect to t. Acceleration is going to be the derivative of velocity with respect to t, or the second derivative of r with respect to t. And speed is the magnitude of velocity, which we've already said is ds dt. Okay, so all of that takes us to this first question, number 1. A particle moves along this curve C with the given vector valued function, which we have in 2 space. Find its velocity, acceleration, and speed at time t. Okay, so our velocity is going to be the derivative of the position function, which would give us cosine of t over 2, comma negative sine of t over 2. So I'm just going to rewrite it. That's our velocity. Acceleration is the derivative of velocity, which is going to give us negative 1/2 sine of t over 2 and negative 1/2 cosine of t over 2. So that's acceleration. And then speed is the magnitude of velocity, which maybe you need to set it up, or maybe you can see from this velocity vector value function that we came up with that the speed is just 1. Okay, and then part B, we are showing that acceleration is orthogonal to velocity. Now, I want to make sure we understand that is for this path only. That is not for all paths, but for this path only. Well, if we think about showing that 2 vectors are orthogonal, we've done that before. Orthogonal means that their dot product is going to be 0. So we need to take acceleration and we need to dot it with velocity. And when we do that, we're going to get negative 1/2 cosine of t over 2 sine of t over 2. Add 1/2 sine of t over 2 cosine of t over 2. That dot product equals 0, which tells us that at any time t, acceleration is orthogonal to velocity. again, for this path only. Let's take a look at another example. An object moves in 3 space so that the velocity vector valued function is 1, t, t squared. Find the coordinates of the particle at time t equals 1. Given that at t equals 0, the particle is at -1, 2, 4. Okay, so we know that our position function is going to be the integral of our velocity function. So we are integrating this 1t squared. So that tells us then that our position function is going to be t, 1/2 t squared, 1/3 t cubed. But then we have some initial conditions as well. So from this information here, we know that r of 0 is -1, 2, 4. So remember, r is a vector valued function, so our output needs to be a vector. So if we use that, that tells us that c is -1, 2, 4. Hence, we get our position function then to be t subtract 1, 1/2 t squared add 2, and 1/3 t cubed add 4. So we want to know, though, what is the position of the particle at time 1. So if we substitute in 1, we're going to get 0, 5/2, 13/3. But then pay attention to what your answer needs to look like. Find the coordinates of the particle. The coordinates of the particle are not a vector. It's going to be a point. So it becomes the point 0, 5, 2, 13/3. And again, just to review what the difference is, what this is saying is we have some vector that starts at the origin that ends or travels to this point. Or travels and ends at this point, really. We're going to do one example that is a little more conceptual, and then we're going to move on. An object with mass m that moves in a circular pattern with constant angular speed omega has position vector, right here. Find the force acting on the object and show that it is directed towards the origin. Okay, so first thing that I want to do is I want to take a look at what is this. So that's in 2 space. Anytime we see cosine t, sine t, or cosine anything t, sine anything t, that's going to be a circle. So what we have right here is we have a circle centered at the origin of radius a. And we have points on the circle P defined by an angle. So that's what we're going to start with. Okay, so this relates to, for you physics people, Newton's second law. Force at time t is equal to ma. Okay, so mass, we already have, that's m. We need a vector for acceleration. So we have our position vector. It's our a cosine of omega t, and then a sine of omega t. So if we take the derivative, then we're going to get velocity. So we get negative a omega sine of omega t. So it's omega, not w. And then we get a omega cosine of omega t. So then acceleration, we take the derivative one more time, and this is going to be negative a omega squared cosine of omega t, and negative a omega squared sine of omega t. Okay, so now we finally can get to that force part. So our force is going to be m times a, when this case is m, multiplied by negative a omega squared cosine of omega t, and then negative a omega squared sine of omega t. Okay, so what I'm going to do is both of these components have an omega squared, so I'm going to factor that out. So this becomes then negative m omega squared, so I'm also going to take out the negatives, times a cosine of omega t, a sine of omega t. And at this point, that should be familiar. This, if we go back to the beginning, is just our position function. Okay, so what did this tell us? It tells us that force can be written as negative m omega squared multiplied by position. So hence, the force acts in a direction opposite to the radius vector r of t, which means it points towards the origin. Okay, and here's why we can see that. Like this black radius that I drew in. So here would be 1 point, right? We have another point over here, let's say. We have our radius vector pointing outwards. Well, this force is saying I'm going opposite to that r, right? Because mass is positive, omega squared is going to be positive. So at any point, we are going the reverse direction, pointing towards the origin. Okay, so while we're on this Newton's second law kick, let's just keep going, do some more Newton, and we're going to look at projectile motion. Okay, so jumping in with projectile motion. Newton's second law, which we already talked about, F equals ma. Okay, so we have assumptions here. First assumption is that we have a constant mass. Second assumption is that the only force that is acting on the object after launch is the Earth's gravity. And then we are also going to assume that the force of gravity is constant because the object is sufficiently close to Earth. Okay, so here's what we have happening. We have our ground here. And we have some object in the air. And that object starts with an initial height of s sub 0. And it has an initial velocity from which it was launched. And then this object is going to follow a path like this and hit the ground. And so that's what we want to be able to model. So we want to be able to model the path that this object takes. So we're going to start with Newton's law. That's F equals ma. M being mass and g being the acceleration due to gravity. Okay, so the way we can rewrite this is F is equal to negative mg j. The negative just means that our object is going down in the y direction, right? So even if it initially starts up, eventually it's going to go down. Now, because of Newton's second law, I can replace that F by ma. M is mass. That's a constant. It's not going to be 0, so I can divide that out. And what I get then is A equals negative gj. So again, if we're looking for position like we have on our figure, we're looking for r of t. That's what we're looking to find. And so now that we have A equals something, what we can do is we can integrate. And when we integrate, we're going to be left with velocity then. So we are integrating negative gj with respect to t. So for velocity then, we're going to get negative gj, let me write it differently, negative gtj plus c. Well, we know at time 0, our velocity is v of 0, like we have on the figure. So where that leads us to then is that v of t is equal to negative gtj add v naught. So then, if I want to find position, again, I'm going to need to integrate. So I'm going to integrate what I have above. So that then gives me r of t is equal to negative 1/2 gt squared j, add v naught t, add c2. All right, so this is really like c1. And again, we're going to have to go back to the figure to get some initial conditions. We know that our initial position is s sub 0, which tells us that c2 is s sub 0 j, which should make sense. The object is moving up initially. So what that gets us then is our position is negative 1/2 gt squared j, add v sub naught t, add s sub naught j. That's often rewritten though, because we have these two j's, oftentimes those will be rewritten together. So what you're often going to see is negative 1/2 gt squared, add s sub naught times j plus t times v naught. Okay, so the question then becomes, how do we express this v sub naught? How do we express that? So that's what we're going to do now. And we're actually going to continue up here at the top to make sure that we have enough room. So we're going to look at this parametrically. If I redraw what I have in the figure above, something like this. Okay, so we can break that down into two components, a horizontal component and a vertical component. So there's going to be some angle that we're shooting this or launching this object off of. So the horizontal component is going to be that v naught cosine alpha. And then our vertical component is going to be v naught sine of alpha. So what we can do then is we can rewrite that vector as v naught cosine of alpha I, add v naught sine of alpha times j. So now what we're going to do is we are going to return to this position vector valued function that we wrote before, and we are going to replace v naught. So I don't know that I gave myself enough room, but let's see how it goes. So this then becomes r of t equals, sorry, this is a little messy, negative 1/2 g t squared, add s sub naught j, add t multiplied by the vector value function above. Okay, so now we have some i's and some j's. So if we can get all the i's together, get all the j's together, that would be great. So if we simplify, this is going to become r of t is equal to v naught cosine of alpha ti add s naught, add v naught sine of alpha t, subtract 1/2 g t squared, all of that times j. Now to do a little clarification real quick, with these sines and cosines, this is cosine of alpha times t, sine of alpha times t. So it's like this. The t is not part of the sine. The t is not part of the cosine. Okay, we're almost done with this derivation, so stick with me. Here's where this takes us. Firstly, we can express the position of x and y separately. So at time t, the x position of the particle will be v naught cosine of alpha times t. The position of the particle vertically, in terms of y, will be s naught, add v naught sine of alpha times t, subtract 1/2 g t squared. Also, we can show the velocity in each direction. So the velocity in the x direction is going to just be v naught cosine of alpha. Velocity in the y direction is going to be v naught sine of alpha, subtract gt. Okay, now that we've done all that derivation, let's look at an example. A basketball is hit with an initial speed of 80 feet per second at an angle of 30 degrees with an initial height of 3 feet. A, find parametric equations for the trajectory of the ball. Okay, so this 80 feet is our initial velocity. 30 degrees is our alpha. Initial height we used as s sub naught. So our x is going to be 80 cosine of alpha times t. So this simplifies to 40 root 3 t. And our y was 3 add 80 sine of alpha t subtract 1/2 g, which is 32 t squared. Okay, so this 32, if you're a physics person, you probably know this. This g is 32 feet per second. And that's what we're mostly going to be using. So we get our y of t then to be 30, add 40t, subtract 16t squared. And this should look familiar from when you've done projectile motion before, probably in Algebra 2, which I know was quite a ways ago for you, and I'm sure you saw it in other places as well. Okay, so we want to know how high does the ball get? So we need to know the maximum of y, so we're going to need to look at the derivative. So if we take the derivative of dy dt, we get 40 subtract 32t. So if we set that equal to 0 to find a critical number or numbers, we get our time to be 5/4 seconds. Now, we are asked, though, how high the ball gets, so I don't care about the time, but I want the position. So if I take that 5/4 and I substitute it back into this position function, I'm going to get 28 feet. Now, here's the problem. We did not show that that's a maximum. We didn't show that that's a maximum. We just said, oh yeah, it's a maximum. That makes sense. We need to show that. So this is a throwback to Calc 1. How do you show that something's a maximum? Oftentimes you're going to use the first derivative test. So if I plug in numbers less than 5/4 into my derivative, I'm going to get positive, then I'm going to get negative, which means that our function is increasing and then decreasing, hence we have a maximum. I do expect that you show some type of work. I don't need a sentence like you often did in calculus. I just want some type of number line that shows me that you did in fact prove that this is a maximum. Okay, how far does the ball travel horizontally? So we want to know when the ball gets back down to the ground, which would be when our y is 0. If you use quadratic formula, you're going to find that this happens at time 2.57. So at time 2.57 seconds, our ball hits the ground. We want to know how far it travels, though, in the x direction. So what we're going to have to do is substitute that 2.57 back into x. And if you trust me, I tell you it's about 178.25 feet. And then what is the speed of the ball when it lands? Well, from above, we know that the ball lands at about 2.57 seconds. We also know that speed is the magnitude of velocity. So first thing that we're going to have to do is find velocity, which is just the derivative of the position function that we wrote above. So that gives us 40 root 3, and then 40 subtract 32t. So speed then, if we're looking at the magnitude, it's going to be 40 root 3 squared, add 40 subtract 32t, so this is where that 2.57 comes in, So that gives a speed of about 81.19 feet per second. Okay, so moving forward, now that we've done projectile motion, we're going to add on a little bit focusing on acceleration. So you can see from the objective at the top, what we're going to be doing is taking acceleration and breaking it into two different components, the tangential and the normal components. So we're going to derive what these components are and then look at some examples. It's often useful to break acceleration into two components, one that is in the direction of the tangent vector and one that is in the direction of the normal vector. So that's what we're going to do. So let's start with a figure. Let's say, again, that we have some position function like this, and we're looking at this point right here. Let's say that our acceleration is out here. Well then, we can draw in, we have unit tangent vector here, might not be to scale. We have our unit normal vector here. So what we're doing with that tangential then, or with that acceleration rather, is we are trying to decompose this acceleration into one that is in the direction of the normal vector. So this is the normal component of acceleration, and one that is in the direction of the unit tangent vector. So that's what we're going to take a look at doing. We are going to define the magnitude of vector as just v. So then what we have, if we start with our unit tangent vector, we know that our unit tangent vector is the derivative of r divided by its magnitude, of course, to make it a unit vector. Well, the derivative of r is velocity, and we are dividing by the magnitude of velocity. So this is really just velocity over v, because we already defined the magnitude of velocity as just plain old v. So what that gives us then is that velocity, if we start here and here, could be written as its magnitude times the unit tangent vector. We also might express it this way. So if we differentiate then to get our acceleration, the derivative of velocity, I'm going to use this one, is going to be the derivative of the magnitude times the unit tangent vector, add v times the derivative of the unit tangent vector. Okay, so then the question is, how are we going to get this derivative of the unit tangent vector? So to get the derivative of that unit tangent vector, we're going to use curvature. So if we remember, there were many ways to calculate curvature, but one of them was the magnitude of t prime over the magnitude of r prime. So that numerator stays the same, but r prime, if you remember, is just velocity. So that's really the same as the magnitude of the velocity vector. So that's just v. So what that gives us then is the derivative of the unit tangent vector, or the magnitude of it, rather, is equal to curvature times v. Another thing for us to know is the unit normal vector. So if we drew it in the figure, we know we have to be using it. That's going to be the derivative of t over its magnitude. So what that also gives us is that the derivative of t is equal to the magnitude of the derivative of t times the unit normal vector. Well, we can substitute in from above, so we get t prime then is equal to curvature times the magnitude of velocity times the unit normal vector. Okay then, so where does this take us? If we go back to this equation that we had above, so we had v prime is equal to v prime times t, add v times t prime. So substituting in v prime, which is really just acceleration, gives us v prime times t plus v, and then that t prime, we're going to use what we just got. So curvature times v times unit normal vector. So this then is v prime times t, add curvature times v squared times the unit normal vector. Okay, so finally, what we get, we can write acceleration then as something times the unit tangent vector plus something times the unit normal vector. And that something comes from here and there. Okay, so the question is, how do we find a of t and a of n in more helpful terms? And also, what does this tell us so far? So, this tells us that the object always moves according to the direction of motion, which is our unit tangent vector, and the direction the curve is turning, which is our unit normal vector. Okay, so let's start from there again. Hopefully we have enough room. Okay, so we have a of t is equal to v prime times t plus curvature times v squared times n. What we have currently is not incredibly helpful. So this is not a very helpful visual. So what we're going to do is we're going to dot it with v. So on the left side, we're going to have v dot a. And on the right side, another way that we can write that v is we can write it as the magnitude times the unit tangent vector. So that's the expression that I'm going to use on the left side. So what I'm saying is this are the same, just different representations. And you're going to see why I'm going to do that in a minute. So that I have v prime times t plus k v squared times n. Okay, so what this gives me then is v dot a is equal to v times v prime t dotted with t plus curvature times v cubed t dot n. Okay, so here's why that's helpful. T dot n, well, those are orthogonal, so that's going to be 0. T dotted with itself is going to give us 1 because it's a unit tangent vector. So hence where this takes us is that v dot a is v times v dot, or v prime rather. Now, from above, we see that v prime is equal to a of t. So we know that v prime is equal to a of t. So a of t then, which is equal to v prime, is equal to v dot a over v, I'm using this, v dot a is r prime of t dotted with r double prime of t over the magnitude of r prime of t. All right, so v is just the first derivative of position. A is just the second derivative of position, and then I'm dividing by speed. So that is how we're going to calculate a of t. Similar idea, a of n from above is curvature times v squared. Well, curvature is the magnitude of r prime of t crossed with r double prime of t divided by the magnitude of r prime of t cubed. So that's all curvature. Then I have to multiply, though, by, ran out of room, by v squared. So what that finally gives us is that a of n, once we do a little canceling. All right, so I can divide that out, it leaves a 1. So that a of n is going to be the magnitude of r prime of t crossed with r double prime of t divided by the magnitude of r prime of t. Whew. So that's what this box here is saying. That's what we just got to. You need to know these formulas. So you need to know these two formulas. And what I want you to notice is they're both scalars. So they're both scalars. This one is called the scalar tangential component of acceleration, and this is the scalar normal component of acceleration. You're also going to be asked for the vector tangential and normal components of acceleration, and all that means is your answer needs to be a vector. And we'll take a look at an example of how to find these. Example number 5. Suppose a particle moves along the path C given by that vector-valued function. In A, find the scalar tangential and normal components of A. So the scalar tangential is going to be r prime dotted with r double prime over the magnitude of r prime. And then the scalar normal is going to be the magnitude of r prime crossed with r double prime over the magnitude of r prime. So either way, we're going to need the first and second derivatives of r. So our first derivative is going to be 1, 2t, 3t squared. Our second derivative is 0, 2, 6t. Okay, so I'm going to have to take the dot product of these. So r prime dotted with r double prime is going to be 0, add 4t, add 18t to the third. So this gives us 4t, add 18t to the third. Then we're going to need the magnitude of r prime, which is the square root of 9t to the fourth, add 4t squared, add 1. So our scalar tangential, then, is that dot product. So 18t to the third, add 4t, divided by the magnitude. So 9t to the fourth, add 4t squared, add 1. And as we can see, this is going to be a scalar when we plug in t. Now, we're going to need to move on to do the normal component. So we're going to have to cross these two vectors. I didn't really organize my work very well, but sorry. So this is going to be r prime crossed with r double prime. If you trust me, I will tell you that this ends up being 6t squared, negative 6t, 2. So then if we find the magnitude of that vector, it's going to be the square root of 36t to the fourth, add 36t squared, add 4. Therefore, our scalar normal component is going to be the square root of this 36t to the fourth, add 36t squared, add 4, over 9t to the fourth, add 4t squared, add 1. Okay, so now we're going to find the scalar tangential and normal components at the point 1, 1, 1. So if we consider this point 1, 1, 1 and look back at r, we notice that this point happens when t is 1. So if we substitute t equals 1 into a of t, we get 22 over root 14. And then our scalar normal component is the square root of 76 over 14, which simplifies to the square root of 38 over 7. Okay, part C, we are moving on to find the vector, tangential, and normal components. So if you recall, when we were deriving, we got A is equal to AT times T, add AN times N. So when it's asking for the vector, tangential, and normal components, it wants this part and this part. And again, we're doing this at t equals 1. So if we start with finding the unit tangent vector, this is going to be r prime of t divided by the magnitude of r prime of t. So t at 1, though, is going to be r prime of 1 over the magnitude of r prime at 1. So this is the vector 1, 2, 3, all over the square root of 14. So then, the vector tangential, I'm going to take this value I got above, so the 22 over root 14, and multiply by the vector. Which gives us then the vector tangential. Sorry, I didn't have the best notation here. There we go. Vector tangential is 11 over 7, 22 over 7, 33 over 7. We also need to find the vector normal component. So this is option 1, is actually find the unit normal vector. Now, that's a little tedious, and I don't particularly want to do that. So what we can also do is go back to this initial equation that we have in black. So acceleration is the sum of the vector tangential and the vector normal components. Well, acceleration I can find. In fact, we already found acceleration. From up above, acceleration is just the second derivative of r, which we found to be 0 to 6t. So our acceleration then at 1 is 0 to 6. What we're going to do is we're going to substitute in here. So we get 0 to 6 is equal to this 11 over 7, 22 over 7, 33 over 7, plus the vector normal. And when we subtract, we get our vector normal then to be negative 11 over 7, negative 8 over 7, and 9 over 7. Okay, and then lastly, just part D, a quick review. Find the curvature of the path at the point 1, 1, 1. So if we remember curvature formula, we're taking r prime, crossing it with r double prime, magnitude of that divided by the magnitude of r prime to the third power. We got r prime of t to be 1, 2t, 3t squared. So then r prime at 1 is 1, 2, 3. For our double prime of t, we got that to be 0, 2, 6t. So again, our double prime at 1 is going to be 0, 2, 6. Cross product, if we remember, we also found above. And that was 6t squared, negative 6t, and 2. That was from part A. So then if I substitute 1 in, I'm going to get 6, negative 6, and 2. So finally then, the curvature at 1, ends up being the square root of 76, which comes from this magnitude, divided by the magnitude of r prime at 1 to the third power. So the curvature at 1 then ends up being 1 over 14 times the square root of 38 over 7. Okay, this is the last required problem on the video. We have one more extra problem in the notes. That's just to review something that we did earlier. So if you think you're good, you can stop here. If not, keep going for another few minutes with example 6. Okay, the position particle of a function is given by r. At what time is the speed at a minimum? Okay, so we should be thinking right now speed is the magnitude of velocity, and velocity is the first derivative of position, which in this case would be negative 10t, negative 1, and 2t plus 1. So speed then is going to be the magnitude of that function. And so we're going to end up with 100t squared, add 1, add 4t squared, add 4t, add 1, which is the square root of 104t squared, add 4t, add 2. Okay, so at what time is speed at a minimum? So to do minimum, we're going to need the derivative. We'll have to take the derivative of speed with respect to time. So we get 1/2 104t squared plus 4t plus 2 to the negative 1/2. And then we have our chain rule, which is 208t plus 4. Any critical numbers are going to happen when this value is 0. Well, conveniently, this is already factored for us. So we want to know, does this factor equal 0 and when? And does this factor equal 0? Well, that first factor is never 0. The second factor equals 0 when t is negative 1 over 52. Okay, so at this point, we would say t is negative 1 over 52 seconds. That being said, that did not prove that this value provides the minimum speed. So like I said earlier in the video, you need to prove that the speed here is a minimum. So you're going to do the first derivative test. We have negative 1 over 52, substituting back into this equation that we have. If we remember this is positive, so really this is what we care about. If we put in a number that's more negative, this will be negative, this will be positive. So our function is decreasing and then increasing again, and yes, we have a minimum. Do you need to draw that parabola? No. So thank you for sticking with me. I know this was a long video. Please bring any questions that you have to class. Good luck.